All right, can I at least help you with the first one a little bit? I mean, notice you got 187. Good job. Let me show you my thinking a little bit too, because even if you landed and you got 187, you're feeling good. You might some of you might have gotten 187. You're still thinking like, I don't know exactly how I got there, but didn't feel great. I don't know. So let me try to explain like my thinking and try to come up with a systematic way of approaching this. I think you agree with my first steps here. Do you agree? In fact, right now I'm kind of I have an answer for omega. It's just in really strange units, miles per hour inch, right? So maybe that's right, but it is actually in fact asking for RPM. So we have a lot of work to do to get there. So I'm about to do like we've been doing many times before. I'm about to multiply my answer by a whole bunch of forms of 1 that make sense to me to change this. So miles and inches need to be resolved somehow, right? So let's multiply by various forms of 1 that work for us. How about 5,280 feet in a mile? And what's the conversion from feet to inches? Let's do that too. 12 inches per foot. All right, now I think if I were to stop here and do this calculation, do you agree that my answer, notice that feet cancel out, miles cancel out, but also inches cancel out. The units that would be left if I do this right now will be nothing per hour, yeah? Or we'll interpret that to mean radians per hour, which is exactly what we want for omega, right? It'll be in like radians per hour right now. All right, but we want it per minute, and we want, what does R stand for, RPM? It's actually revolutions or rotations. So we have some work to do still. All right, so hours need to be turned into minutes. Hour is on the bottom, isn't it? So I need to have that on the top. Hour. Over 60 minutes, there's 60 of those in an hour. Min. All right. So now it's in, what is it now in? It's in nothing per minute. Or as we just talked about, it's in radians. Isn't it radians per minute? So we still need to do one more thing, and that's to get this into revolutions. So right now it's radians per minute. So let's do revolutions over 2 pi radians to introduce that. Won't the units here then be revolutions per minute? Just to make this clear. Miles, hours, inches, feet. Yeah, in the end, won't we get revolutions on the top, minutes on the bottom? So just run that calculation, and I guess you'll get, like I said, 187 revolutions divided by minutes. To 3 sig figs. It's not exactly that, right? So that might be how I run it in a systematic way. And notice, I always kind of, you can do it whatever way you want. If you do intermediate calculations along the way, you'll have to store values in your calculator. Be careful not to round. I like my method because it's like I can work it all out and then I can just type it all in. You can do whatever you want as long as you're getting the right answers. I don't mind which way you prefer to do it. I can understand if you want to do it piecemeal too, because it might be a lot to think about all at once. But I like kind of getting my answer and then doing like a whole mess of unit conversions. That's my take on it. Can I at least? Is that okay? Everyone good on that now? Which one? This part here. So would you agree without that it'll be in radians per minute? It'll be like nothing per minute. And that's what omega is naturally in. It's in nothing per minute, right? Some radians per minute. That's what omega is. So we still need to convert it to revolutions per minute, right? So how many radians are there in a minute? Well, we need to divide by 2 pi. If it's there, it's there. Yeah. I don't know. So there, yeah. All right. Is it okay if I actually get you started a little bit on the next one? I want to make sure that you're like at least headed in the right direction. Some of you have already struggled with a little bit, which is great. But it is a little daunting to see this picture where we have like 3 things rotating, don't we? And actually there are more than that rotating. We've also actually got like a whole bunch of gears in the back and on the front. We got the pedal rotating out here too. Whoa. Okay, it's like that video that we watched yesterday with the bike dots. All right, so before you do anything else, I always like to give you the hardest parts of the problem I like to give away. Front gear, radius is 3 inches. You're welcome. Back gear, 1.5 inches. You're welcome. And the tire is 14 inches. Okay. You're welcome. Okay. I know. Okay. So then the only other, that's all the given information in the problem, except in part A it does tell you how fast you're pedaling. And what kind of velocity is that? 80 RPM, what is that? That's angular, isn't it? That's telling you how, it doesn't actually tell you how far your foot is traveling. It's telling you how fast your foot is rotating around the pedal, okay? So for the front gear, what's true about the front gear and the pedal? What's their relationship? What's the same about those two things? Can we use this information about how fast we pedal to fill in something in the first line of this table? If so, what? Yeah, the angular velocity should be the same. I mean, you're pedaling out here, but the pedal is welded to, all the gears are welded together on the front here, right? They all rotate together. So they all have the same angular velocity, don't they? No matter, all the gears and the pedal on this front set of sprockets here. Which, by the way, I'll draw this on the board here. This is an important second situation in your life, maybe, right? I think yesterday we talked about this idea that when is the linear velocity the same for two rotating objects, or gears or pulleys? And I think we had two interlocking gears, and we said for gear 1 and gear 2, we have V1 equals V2. I think we maybe said this too in your homework. You had one like this. Two pulleys connected by a band of some kind, or two gears connected by a chain. Those have the same linear velocity. Also, if you have say you have this sweet dune buggy thing that you I don't know, it's awesome. Okay, it's legit. I don't know. Maybe it has I don't know. What does the dune buggy look like? What's true about the two tires? Well, they have the same linear velocity, don't they? Even if they have different sizes, they're hitting the ground at the same rate, aren't they? So all those situations, we have the same linear velocity for both the rotating things. The other situation, though, that we're talking about right now, is when you have rotating things that are all fused together on the same axle, right? So there we have omega 1 equals omega 2 for those two things, don't they? If one rotates, so does the other, right? So that's this is important as we go through this table to think about that. All right, so what do we put there? 80 RPM is the front gear angular velocity. Except it says let's put it in radians per minute. So can you do the conversion on the fly? What would that be? 2 pi times that, so it'd be 160 pi radians per minute, or just unitless. Okay. All right. So I think we're doing well. By the way, I do encourage you to leave the pi in there for now until we're done, just because in our final answer we might not have that. But what can you do now then? We're trying to fill out the table here, right? V equals R times omega. So can we pull something else out? Yeah, I think we can get this, can't we, by doing what? Multiplication will get us there. So here's what I'm going to do. I'm going to calculate that value, but I'm not going to tell you what it is, okay? You can do the multiplication at home. There you go. What then, though? Once you fill out the first row of the table, that'll be great. How do you then fill out more of the table? We need another, understanding, because we're trying to get down now to the back here. Think about the things we just talked about on the board. Yeah.
The front gear and the back gear have the same relationship as the very top doodle on your V1 equals
Okay.
side.
Yeah, good. I like that.
So, they will have the same linear.
Yeah, they're the same. Right, exactly. They're connected by a chain, so points on the outside of the two gears and points along the chain should all be moving at the same speed if they're really going to interlock properly. Right? So that means copy and paste, doesn't it? Whatever answer you get here should be just the same here. What will that allow you to do then? Yeah, maybe you can fill out now the angular velocity. Then how do we get to the third row? Yeah, Shivani.
Isn't the angular velocity equal to the tire equal to the angular velocity?
Yeah, they're actually, again, they're welded together, all the gears on the back and the whole bike tire and everything are all like one piece. So they definitely rotate together. You can copy paste there once you get your answer. And then of course I think we'll be able to calculate this. Yes? You see the direction I'm zigzagging through the table? Do you like that? Yeah? Cool. You get like one thing that helps you fill out the next. Now, why in the end are we maybe interested in answering what the linear velocity of the tire is? Well, because that's your speed, isn't it? On the ground, like that's how fast you're actually going, isn't it? So I hope you understand that through this chain of like calculations, we've talked about how fast you're pedaling, and we've told you exactly what that means in terms of your speed on the ground for the bike, right? So, does that make sense? Why that would be like a useful thing to even ask? If I pedal 80 revolutions per minute, I will be going, apparently the answer to this, by the way, on B is 13.3 miles per hour. So see if you don't get that, right? I think it's an interesting thing to think about. Now, I will warn you on C, B isn't not too bad. C, basically, I didn't give you a table, but basically asks you to run this entire set of calculations again, but in reverse, doesn't it? This time I'm giving you the speed on the ground, I'm asking you to like zigzag back up through the table and give me what the pedal rotations per minute should be. And number 3, the next page at the top, is another problem very similar to this. I just didn't give you a table, okay? So if you want to draw a table, you can, okay? My last class did complain about the fact that this is a lot of homework. So if you want to do everything.